Okay, today we are talking about arithmetic and geometric theories, which is different from a sequence. So a series is the indicated sum of the terms of a sequence. A series is the sum of the terms of a sequence. So a sequence is a list of numbers. A series is the sum of those numbers. We add them all up together. So with a sequence, you're going to have a list of numbers, and with a series, you're going to have one big number at the end where you added up all of the numbers in the sequence. All right. Like a sequence, a series may be finite or infinite, so it could stop or it could go on forever. And a series may be written using sigma notation, also called summation notation. And that's this funny thing right here. It's called a sigma. That is the Greek letter. And in math, we use that to indicate a sum. So for any sequence, the sum of the first n terms may be written like this, which is read the sum of a sub k from k equals 1 to k equals n. Okay, so what you need to know about this notation is that this is our formula. That's where we get the term from, and you're going to see that when we start doing the examples. This a sub k is our formula, and so the variable we use for that is usually a k, although not exclusively. The k equals 1, this is our start. So this series right here starts at 1. That's our starting point. And then n is our ending point. That's where we end the series. Okay. And so if it is a finite series, this n value is going to be a number. It might be 10 or 100 or 2,000. But if it's infinite, this n will be an infinity sign. Okay? All right, so let's just look at the examples because this stuff is a lot easier to deal with when we're actually talking about specific problems. So they want us to find the following sums. They want us to find the sum from k equals 1 to 5 of the series 2k plus 1, okay? And so what they want us to do is they want us to find the first term all the way to the fifth term and then add those together. So we're going to make a list of terms first. So when k equals 1, the term that I have is 2 times 1 plus 1, which is 2 plus 1, that's 3. When k equals 2, that's my second term. I have 2 times 2 plus 1, which is, what is that, guys? It's 5. When k equals 3, we have 2 times 3 plus 1, which is 7. When k equals 4, we have 2 times 4 plus 1, and that's 9. And then when k equals 5, we have 2 times 5 plus 1, which is 11. And those are our first 5 terms, right? This is my first, second, third, fourth, and fifth terms. What I have right here is a sequence. The sequence is 3, 5, 7, 9, 11. The series is going to be the sum of these numbers. And so what we're going to do is we're going to, after we've found those first 5 terms, we're going to take those numbers and add them up. So 3 plus 5 plus 7 plus 9 plus 11. And when we add those numbers up, what do we get? 35. That's 35. And so the sum of the first 5 terms, which is what this is saying, find me the sum of the first 5 terms using this formula right here, is 35. For number 2, we're finding the first 4 terms, right? We're going to start at the first term and we're going to go to the 4th term. And so we're going to list those terms, and then we're going to add them all up and find the sum of those terms, which will give us the series value for this. So when j equals 1, that's my first term, this is 1/2 to the first power, which is 1/2. When j equals 2, this is 1/2 to the second power, which is 1/2 times 1/2, and that is 1/4. 1/4, yeah. 1 times 1 is 1, and 2 times 2 is 4. When j equals 3, that's my third term, and that's 1/2 to the third power. That's 1/2 times 1/2 times 1/2. 1 times 1 times 1 is 1, and 2 times 2 times 2 is 8. And when j equals 4, that's our fourth term, and that's the last term that we've been asked to find because we're supposed to start at 1 and end at 4. That is 1/2 to the fourth power, and that's 1/2 times 1/2 times 1/2 times 1/2, which is 1/16. Now, we are asked to add all of these numbers up. You are allowed to use a calculator to do it. I'm going to do it here without a calculator. So if I want to add all of these numbers up, I need a common denominator, right? They've all got to have the same number on the bottom. And so to do that, I'm going to go with the biggest number I see, which is 16. So 1/2 can be written as 8/16. 1/4 can be written as 4/16. 1/8 is 2/16, and then 1/16 is already there. And so I add those all together. 8/16 plus 4/16 plus 2/16 plus 1/16. And when you add those all up, we're over 16. 8 plus 4 is 12, plus 2 is 14, plus 1 is 15. So it's 15/16. And again, the sequence for this would be 1/2, 1/4, 1/8, and 1/16, but the series is the sum of those numbers. And so the answer to this is 15/16. All right, looking at number 3, they want us to start at 3, because that's a t equals 3, and go to 6. All right, so we don't have to start at 1. We're starting at 3 and going to 6, and we're going to add those terms up. So when t is 3, my term in the sequence is 3 squared, which is 9. When t is 4, my term is 4 squared, which is 16. When t is 5, my term is 5 squared, which is 25. And when t is 6, my term is 6 squared, which is 36. And we can stop there. We found the terms from 3 to 6. Now we need to add those up. So it's 9 plus 16 plus 25 plus 36. And when you add those numbers up, what do you get? 86. So the answer to this series is 86. When I add all those terms up, I get 86. All right, guys, so for this one, I need to find the sum to the 6th term of this series. Now, what do we notice about this series? Right there, it has an infinity. That means it's infinite. That means it's infinite. And that's okay, because we are not asked to find the sum to infinity. We're just asked to find the sum to 6. That s sub 6 means find the sum of the first 6 terms. And so we are going to start at the first term, and we're going to go to the 6th term. So when k equals 1, my term is 5 times 1, which is 5. When k equals 2, my term is 5 times 2, which is 10. When k equals 3, my term is 5 times 3, which is 15. When k equals 4, my term is 5 times 4, which is 20. And when k equals 5, it's 5 times 5, which is 25. When k equals 6, it's 5 times 6, which is 30. And so that is my sequence, 5, 10, 15, 20, 25, 30. To find the series value, I add it all up. So 5 plus 10 plus 15 plus 20 plus 25 plus 30. 5 plus 10 is 15, plus 15 is 30, plus 20 is 50, plus 25 is 75, plus 30 is 105. So that is 105. All right, so that is how you would calculate the sums if you are given the formula. And if we are dealing with small numbers of sums, so we're finding the sum to 4, like we did in number 2, or the sum to 6, like we did in number 4, this works just fine. But what if I wanted to find the sum to 15? Then this might be kind of cumbersome, right? So that's when we employ formulas. So if you turn your page over, arithmetic sequences with common difference d and sum, so summations of this. You can use this formula or this formula to find the summation to a point, okay? So this formula right here, the sum at n is equal to n, so the number you want to go to, the term you want to go to, times your first term plus the term at that point divided by 2. Alternately, you can use this formula here. And you can say, okay, my sum at n is equal to n, the number I want to go to, times 2 times the first term plus the common difference times n minus 1 over 2. Now, do you recognize this, guys? Anything about this formula right here? N minus 1? That maybe the d times n minus 1? Maybe this whole thing in parentheses right there? Do we recognize that? That's our formula from yesterday. That's our sequence formula, right? That's our sequence formula. Okay. So here's the deal. When you have summation notation, this formula is always going to be easier to use. So when you have that sigma, use that formula. Okay. When you have a list of numbers, this formula is the formula with the 2a sub 1 plus d times n minus 1. When you have a list, you want to use the second formula. Okay. Guys, we do not expect you to memorize those formulas, but we do expect you to know which formula you're supposed to use and implement that formula correctly. All right. So here we have 2 examples. There's a difference between these problems, right? Here I have the summation notation, and here we just have a list of numbers. As I said, guys, when you have summation notation, this formula is easier to use. Okay, and so we're going to use that formula. I need to identify all of the pieces of this formula that I need to plug in, though. So to find the sum at term 10 for this series, I need n, which is the number I'm going to, and that is 10, the sum at 10, so n is 10. I need my first term, and we find our first term by plugging 1 into this formula right here. So 3 times 1 plus 1, and that's 4. And then I need my term at n. So I need my 10th term, a sub 10. And so that's 3 times 10 plus 1, which is 31. And then I just plug those values into this formula. So S sub 10, my sum at 10, is equal to 10 times the first term plus the 10th term divided by 2. This is 10 times 35 divided by 2. That's 350 over 2, which is 175. And that is your answer. All right, so guys, for number 6, instead of having this formula here, what we have is a list. And when you have a list, it's easy to find the first term, right? And it's easy to find the difference, that D value, but it is less easy to find the term that you're looking for. So we want to find the sum at the 34th term, the sum at the 34th term. I don't want to have to expand this series out to 34 terms. So we're going to use this formula right here. And in order to do that, we need to identify all the pieces of this formula. So I'm looking for the sum at 34. And so I need the term number, which is n, and that's 34. Right, they told us that. I need the first term. And so here the first term is 12. So a sub 1 is 12. And then I need that common difference, the difference between the terms. And so we look at our terms from 12 to 7. How do we get from 12 to 7? What's our difference there? It's -5, right? We subtracted 5 from 12 to get to 7. And we want to make sure that's a common difference. We want to make sure we can actually use this formula. So from 7 to 2, that's another -5. And from 2 to -3, that's another -5. So that's a common difference. It's the same every time. So my D is equal to -5. And then we just plug it all into this formula. So the sum at 34 is equal to 34 times 2 times 12 plus the common difference of -5 times 34 minus 1 all over 2. And that looks like a big old complicated formula, but it really isn't, guys. We're just plugging in values here, okay? And you are again absolutely permitted to throw this into a calculator and calculate that value. This is 34 times 24 minus 165 over 2, and it's the whole thing over 2. And when you calculate that, I know that's a big number, right? It looks like a big number because it's going to be over 100 multiplied by 34. It's a big number. It's -2,397. Now, when I did this problem the first time, I was just going over it myself this morning. I thought, that can't be right. I'm finding the 34th term, and if I subtract 5 every time, I mean, 5 times 34, that's not 2,000. Why is that -2,000? That seems so weird. Does anybody know why that's -2,000? Like, what was wrong with my thinking? Now, if I just have a list of numbers, 12, 7, 2, -3, if I just have a list of numbers, that's a sequence, right? But a series is the sum of all the numbers, right? And so I'm not just traveling -5, -5, -5, 34 times. every time I make that minus 5, I then add that number to my sum. So my first term is 12, and then my second is 7, and when I am done with my second, the sum at that point is 19. It's 12 plus 7. My third term is 2, so my sum at 3 is 21, right? My fourth term is negative 3, so my sum at 4 is 17. And so we, at this point, because our terms become negative, we start going down and we keep subtracting numbers and subtracting numbers. So while if you did this calculation and extended out these numbers with the pluses, you'd get to the last number you add, I think, is negative 153. That's the sequence. But with the series, every time we have a negative number, we add it on. And so that's how we get to 2000. Every time we have it, we add them all together. So every number is added to every other number, and that's how we get to the negative 2000. All right, guys, let's look at 7 and 8 really quickly. Now, for geometric sequences, we are only going to use one formula, okay? And that formula uses the first term and then that R value, which is our common ratio. And so you need to know the term number as well, but we just use this formula right here. So you need to know the first term, the common ratio, and then the number that you're looking for. All right, so I want to find the sum at term 7 of this series right here. So I need my first term, which is 1. I know that I'm going towards 7. N is 7. That's where I'm finding my sum. But then I need my ratio. So we need to know, what am I multiplying by every time to get this set of numbers? So from 1 to negative 0.8, what did I multiply by? Negative 0.8. And if I go from negative 0.8 to positive 0.64, that's a negative 0.8 multiplication as well, right? And so my common ratio is negative 0.8. And so if I want to find the sum at 7, I just plug those numbers into this formula right here. So my first term, which is 1, times 1 minus, and this is important, the R value needs to be in parentheses. So negative 0.8 in parentheses, and then raised to the term you're going to, in this case it's 7, and value is 7. So that needs to be in parentheses. It's very, very important. What does this need to be in? Is that important? Yes. All right, and then you divide by 1 minus the R value again, and again that should be in parentheses, 0.8. So I'm subtracting it no matter what it is. In this case, it's a negative number, so instead of subtraction, we're going to have addition there. Again, using the calculator at this point is completely acceptable. And when you do, you get 0.672064. Is the top supposed to be in parentheses?
Yeah, there's like a parentheses after the 7.
Yeah, so the 1 minus R to the n power is in parentheses. Here's 1 minus R to the n. It should be in parentheses. The parentheses that I was talking about that are super, super important, though, are the ones around that number right there. Okay, guys, and then number 8, the last one, is the sum at term 6. So we need our first term, which is 3 over 4 to the first power, and that's just 3/4. So we're good with that. I need to know the number I'm going to, n equals 6 there, so they told us, right, the sum at 6. And then I need my ratio. And so for the ratio for these, we're going to have to find a few of the terms to make sure that we've got the right ratio. So I know my first term is 3/4, and then my second term is 3 over 4 squared, which is 3 over 16. And my third term is 3 over 4 cubed. That's 3 over 64. Although that is less important to seeing the pattern than this. What are we multiplying by every time? We went from 3/4 to 3 over 16 to 3 over 64. What's happening? What am I multiplying by 4? I'm multiplying the denominator by 4. So I can't say multiplying by 4. We're actually multiplying by 1 over 4. Because it's the denominator that's changing, right? So we've got to say I'm only changing the denominator. So it's 1 over 4. And so our common ratio for this is 1/4. Okay. And so to find the sum at term 6, again, we just throw these values into this formula here. So that is 3/4 times 1 minus 1/4 to the 6th power all over 1 minus 1/4. And again, you are permitted to use a calculator to do this. And that's 0.999756. Which is awfully close to what? It's awfully close to 1. All right, and we'll talk about why that's awfully close to 1 and what that means tomorrow.